Now let's try to see how to delete an entry from the B plus tree. So now we have seen the deletion from B tree. It is exactly same as B tree only, B tree deletion, with some minor modifications. The minor modification comes in place of, see, if you look at B tree, we are going to have an entry only in one of the nodes. But coming to the B plus tree, we will have an entry in the leaf, as well as we might have the key in one of the non-leaves also, right? Somewhere you are going to see it. Sometimes it might appear. It is not that always you are going to have it. It might appear. Therefore, there is a chance that a node or a key might appear in more than one places in case of B plus trees, and coming to B trees, a key will appear only in one node. That is the only difference. Now, keeping that in mind, we might have to just modify the procedure that we have used in B trees, right? I'll try to explain you the procedure first. Later I'll take an example and explain you how to do that. Okay, let's see the procedure first here. Now, whenever we are going to delete an entry, we have to go till the leaf and find out where that entry is actually present, right? See this, start at the root and find the leaf L where the entry belongs, which means you are going to travel till the leaf from the root and find out where it is actually present. Now once you find out that, then remove the entry. From that you are going to remove the entry. After removing it, now you have to see how many entries are remaining in the leaf. So whenever you are going to delete, you have to always be careful about the underflow condition. Underflow condition means, if you have to see that the minimum number of required entries should always be present there, right? Now what I mean to say is, if L contains at least p by 2 minus 1 entries, then it is done. Why? Because this is the minimum number of entries that we told you, earlier we discussed that this is the minimum number of entries that have to be present in the leaf. Now in case if this is not present, then we might have to call it as underflow. If there is no underflow, then the algorithm is almost done, right? Then small part is remaining. I'll show you what that part is. So what I mean to say is, after deleting the entries, after deleting one entry in the leaf, if there is at least p by 2 minus 1 entries present in this leaf, then there is no problem. You can leave it there. In case if the number of entries is less than this number, then we can call it as an underflow, right? When will there be underflow? If L has only p by 2 minus 2 entries, right? Which means instead of this, if it is after removing it, if it is p by 2 minus 2 entries. So why do we get this case? Already this leaf is having exactly the minimum number of entries required, and from that you have decreased one of the entry. Therefore it will be underflow now, right? Now whenever you have p by 2 minus 2 entries, then what we can do is, we have two options. One option is, if any of the siblings, if they have enough number of, let's say these are the siblings, right? So what do I mean by sibling is like this, okay? Now let us say there is a sibling here and there is a sibling here. Now if any of the siblings, if they are having nodes which and if they are not having any underflow, right? What I mean to say is, if this one is having p by 2 and if this one is having p by 2, or any one of them is having p by 2, then you can borrow one entry from there and you can put it there. Now what will this one become? P by 2 minus 1, right? And what will this one become? P by 2 minus 1. Therefore both of them will not be having underflow. But then while moving it, you should be careful that you have to change the entry here. I'll show you with example what has to be done there, okay? But then remember that if any of the sibling is having enough number of entries, enough number of entries means greater than or equal to p by 2, right? In that case you can just merge, take them and rearrange it, right? That is called borrowing. See this? In that case, try to redistribute borrowing from the sibling. What is sibling mean? Adjacent node with the same parent. Got it? When is it possible? Only when they are having enough number of entries. In case if it is not possible, then the redistribution will fail. So if redistribution fails, which means the siblings are not having p by 2 and p by 2, or at least p by 2 entries, then what we should do is, we should try to merge, right? In that case of merger, what we should do is, when you are merging these two, then 2 pointers are not required and this entry is not required. You have to make the appropriate changes at the parent. Got it? I'll show you with examples what that changes are, right? So if redistribution fails, then merge L and a sibling. Take a sibling and you merge with that, right? Now come to this. Now in case if merge occurred, then the corresponding entry from the parent must be deleted. So what I mean to say is, if you are going to merge, let's say these two, this is a leaf and this is a leaf. If you are going to merge these two and if you are going to make it as a single leaf, then there is no need of entry here and there is no need of 2 pointers, right? This entry can be deleted and you can have just one pointer pointing to this. Got it? In that case, you might have to do the required arrangements there, right? Required modifications. Now what happens is, whenever you delete an entry from here, now there could be a possible underflow in the parent, right? In that case, you might have to again do the same kind, either merging or either redistribution, whatever is possible. So in that case, what happens is, if you keep on merging till the root, then the height of the tree might reduce, right? Now see this, the merge could propagate to the root, decreasing the height. So if it is going to propagate till the root, then it is going to decrease the height of the tree. I'll show you with an example how it is possible. And next one is, if the deleted entry is present in internal node, replace it with the in-order successor. So whatever node you are going to delete, let us say you have deleted a node from here, okay, and if that node is present here as well, right, or somewhere you are going to find it, not just in the parent, it might be present on the way to the root, right? If you are going to travel from the leaf containing the entry towards the parent or towards the root, on the way you are going to find that entry somewhere. It is not that always you are going to find it. In case if you find it, what you should do is replace that particular entry. Why we should replace it is, since it is not going to be there in the tree, it should not be present anywhere. Got it? So you have to replace it with the in-order successor. So what is the in-order successor is, now let us say this is a tree, right, and we have many levels there, right? Now if I have to replace this entry with in-order successor, then you have to go to the right subtree of that particular entry, this right subtree, and go to the leftmost entry in the leaf and you take it and put it there. So I'll show you with example how to replace it. Okay, that is called as in-order successor. So this one is similar to that BST. In BST also we do that. Either we replace with the in-order successor or the in-order predecessor. But here we go with the in-order successor because once I take this entry and put it here, it means that that particular entry is present in the right subtree. Got it? This one we have already seen in the definition of B plus trees. Whenever you have a key here, it means that if you are going to look for that entry, you can go to the right subtree and search it. That is why we are going to replace it with the in-order predecessor, successor here. Okay, so I'll show you with an example how to do this one.